So then, another very important geometry topic is the idea of similar triangles. But let me start with similar objects in general, not just triangles. So two geometric objects are similar if they are either identical, which in geometry we say congruent. So one can be reflected, rotated, and translated into the other one, basically identical. Or one of them is an enlargement of the other. That, in general, implies two things. One, angles are the same, and sides are proportional. So if we have a triangle where, let's say this is 80 degrees, and this is 60 degrees, and this is 40 degrees, then any triangle similar to this will have the same angles. So when I say same angles, that doesn't mean that two angles in the same triangle. It means there are corresponding angles. It's called corresponding. So when we enlarge, say this, and we just slightly enlarge this one, then this point will correspond to this point. Same with things. If that point is A, this should be line segment A. Sometimes with similar objects, we would use the same letter with A prime. And so if this is B, that would be B prime, and this is C, this would be C prime. And so if we were to, now let's put just random numbers here. If this was, say, 5, and this was 6, and this was 7, and by the way, that's not possible because 3 angles determine the ratio, so it's probably not that. But let's just go with it for now. And if you wanna just shrink it down to half, then the angles will remain the same, but the sides, well, the side that used to be 6 will now have to be 3. The side that was 5 will be now half of 5, which is 2.5. Okay, I really dislike my picture right now because 2.5 seems longer than, don't like that. So let me make this 8. So then the side that used to be 8 would be 4, and the side that used to be 7 is going to be 3.5. So that's what it means, sides are proportional. So this is what it takes for objects to be similar. And usually you have to have them both so that you can establish similarity. So in general, so that means that two objects are similar if and only if we have both of these. The angles are the same and sides are proportional. So let me show you why angles alone are not enough. Say you have a square with sides 1, 1, and 1. You can have a square that has sides 1.5 and 20. The angles are the same, but these two are obviously not similar. And proportional sides are not alone. Proportional sides alone are not enough. We can start again with the square 1, 1, 1. And now let's double each side, but also kind of slap it around a little bit. This is called a rhombus. and it's a special case of a parallelogram. A parallelogram has two pairs of parallel sides, but in case of a rhombus, all four sides are the same. Let's say 2, 2, 2. Clearly, these two are not similar, although corresponding sides are proportional. That's in general. But triangles are relatively simple. In case of triangles, just one is enough. So if you prove, and this is by far the most frequently occurring, if you take two triangles and you prove that they have the same angles, and usually you can stop after two angles, right? Because the third angle, if angle A and angle A prime is the same as angle B and angle B prime, that forces C and C prime to be the same angle that when added to the previous two, you get 180. So just two equal angles, two corresponding pairs of equal angles is enough to say, okay, these two triangles are similar. And then we can use that fact to find ratio problems to solve for sides. Or if we prove that we have two triangles and, well, the shortest side double, so we have two triangles and we can show that all three sides of the bigger triangle is twice as long as all three sides of the smaller triangle, then in fact they are similar, and therefore we can conclude that they have the same angles. And there is a third case. So two triangles are similar if, so the first, and by far this is the most common, we chase down angles and then we use similarity to find sides. Two triangles are similar if one, they have the same angles. And I just kind of want to go back to the idea of slope because there are lots of similar triangles there. Find just one page of the coordinate system. That's some, so anytime you pick 2 points on the line, you're going to get a right triangle where, well, what is obvious here is the ratio between the horizontal and the vertical side remains the same. That's the slope. That's the slope. And then why are the angles the same? Well, these two angles are obviously the same and they have each right angle. Right? Why are these two angles so the same? Look, both lines forming the angle are pairwise parallel. Oh, it's the transversal case. So lots of similar triangles in our idea about slope. Okay. So second, corresponding sides are proportional. I guess now I'm going to say this. So there are two ways to get to that. Imagine that we have a right triangle. Let's take a nice one that we know, 5, 12, 13. And I'm going to use trigonometry, which is in your future, to find this cute little angle here. This is a right angle. So this angle is 22.6 degrees. in trigonometry, you will see that there is something sad that happens. If the sides are nice, the angles are terrible. If the angles are nice, the sides are terrible. Often they're both terrible. So you can't just win. But if you know one angle in a right triangle, you know all three angles, right? It's a right triangle. So we know that this angle is 90, and then this angle is 22.6. This has to be the one that when added to these other two, we get 180. So these two, it's just basically these two better add up to 90 so that the plus 90 will give 180. So it's what? 60, no, 70. 7.34. Okay, all right. So, and let me call this A, B, and C. And now let's double this triangle. So then the side that used to be 5 is now 10. And let's call it B prime. And A prime is going to be, instead of 12, it's going to be 24. And then C prime better be 26. Okay. So there are two ways to express similarity, and they're both very useful, very important. One of them is you can think of the magnifying factor or scale factor. In this case, the magnifying factor from here to here is 2. Magnifying factor, that looks weird. Which is 2. In this case, that would be the ratio between 10 and 5, but now I'm going to say B prime over B and A prime over A. Right? 24 over 12, that's a 2. 10 over 5, that's a 2. And if you take this, so this is not so difficult because on one side there are the letters, and either on the top are the bigger ones or the bottom. So you cannot mix and match. The left-hand side is all the B's, the right-hand side is all the A's, and the numerators are the big ones. When we multiply both sides by AB, what we are going to get is AB prime equals A prime B, which is not something you have to memorize. This is something that you just practice to set it up. But there is another way to think of this, and that is basically, well, the ratio from this side to that side, that ratio should be preserved. So B over A, which is 5 over 12, should be the same thing as B prime over A prime, which happens to be 10 over 24. And you see these two are the same. So that's a little bit different. You take one fraction of two sides, and that fraction, that ratio has to be preserved. But if we cross multiply, or if we multiply both sides by A prime, we get A prime B equals AB prime, which is the same thing we had here, you see? So they're just as correct, and half the time, this is gonna be more useful for you, half the time, the other one will be more useful to you. And you can always take the reciprocal of two sides, because in geometry problems, we don't have to worry about 0 in the denominator. These are all positive numbers. These are distances of actual triangles. Sorry. Okay, any questions? So let's grab this 5, 12, 13 triangle. And let's draw in a side, which I'm gonna call X, and this, which I'm gonna call 4, and this, which I'm gonna find Y. What is X, what is Y? So the thing is that these two triangles, well, which two? Let's say this is A, B, C, D, E. And so triangle ADE triangle ADE and triangle ABC are similar because they have the same angle, same angles. Hold on, my audio. Okay. So why are they similar? Well, they have the same angle. And two angles are enough. Well, there is a right angle in both of them. And then this angle, they literally share. It's not just the same measure. It is the same two lines that form it, right? Because two pairs of angles are the same. So as I said, we use that the triangles are similar using chasing down angles. And once we have that, we use it to find proportional sides. And so now we can use proportions, ratio problems to solve for missing sides. And if you think about it, well, I don't know if you see it, but this side, it corresponds to this side. They're not twisted and turned. So this is kind of easy because the corresponding side, the horizontal side corresponds to the horizontal side. The vertical side corresponds to the vertical side. And so it's not so difficult to see that 4 becomes 12. And that means we tripled every side. So this should be 1/3 of 5, and this should be 1/3 of 13. Done. But to write it down a little bit more precisely, you have to make sure that you use that you don't mix and match between the two different ways we can express ratios. And so one way to do that is to write down what we're going to use. So we can say, I'm going to compute the ratio of the horizontal side. Now let me do vertical first. Of the vertical side versus the horizontal side. Now, in the small triangle, in the big triangle. So in the small triangle, the vertical side is x, the horizontal side is 4. So we have x over 4. And now it has to be the same ratio in the other triangle, where the vertical side is 5 and the horizontal side is 12. And now forget the whole thing, forget the picture, just solve for x here. All we have to do is multiply both sides by 4. So x is 4 times 5 over 12, which is 5 over 3, which is what? Almost 2, 1 and 2/3. So that's one safe way to make sure we get the right, we get the ratio right. And then we can look at, okay, if we want 5, we have to involve the hypotenuse. So we can say, well, and the horizontal side is the most useful, right? Because it has both the small one and the large one. And even though we found x, but it's yucky, it's 5 over 3, maybe we're better off with 4 and 12. So we're gonna compute the hypotenuse divided by the horizontal side. And you don't necessarily have to write these things, but make a decision and then follow it on both sides. Why did I put the hypotenuse up? Because I don't want to have to dig out the unknown from the denominator. I want y to be above and 4. In the small triangle, the hypotenuse is y, and the horizontal side is 4. And on the big triangle, the hypotenuse is 13, and the horizontal side is 12. And again, all we have to do to solve for y is multiply both sides by 4. So y equals 13 over 12 times 4 is 13 over 3, which is 4 1/3. Now, you should have this technique because the ratio is not going to be as forgiving as triplet or take it, just divide it by 3. It could be 2 multiply by 2, divide by 7. So something more complicated, and you should have the algebraic machine to address that. Okay. So you have to find the side x, and I like this one because x is not a side of any triangle. So no matter what similar triangles you compute, x will never stand alone. What we have to deal with is a side like this. So the first thing should be is find this side. Can we find that missing side there? Of course, there is the Pythagorean theorem, right? These are still right triangles. Find AE, 3 squared plus 4 squared under the square root is square root of 25 is 5. So this side is 5. And now we just have one letter to find. Maybe I can squeeze it here. X. And X is part of the hypotenuse of the big triangle. Oh, so which two triangles are similar? Triangles ACD, ACD, and ABE are similar. Why? They have the same angles. Literally share this one, and they both have a right angle. And so the ratio that we should come up with should include x. So that means hypotenuse. So we're going to look at the hypotenuse over, say, the horizontal side, in the small one, in the big one. Now, in the small triangle, the hypotenuse divided by the horizontal side is 5 over 3. The same ratio in the big triangle is not x. It's 5. It's not x. It's not 5. It's x plus 5, right? And the horizontal side is not 3 or the other 3. It's 6. So you're going to have to start working on the ratio because it's not going to be exactly just one letter. In this case, x plus 5 is the hypotenuse and 6 is the horizontal side. And so you might suspect that we double the small triangle, right? 4 to 8 and 3 to 6, that looks like 5 to 10, and then subtract 5. This should be another 5. So it might be suspicious, but as I said, numbers will not always be so kind. So if you multiply both sides by 6, then we're going to get 5 times 2 is 10, and x plus 5 in the other side. So 10 is x plus 5. So x is 5. Any questions? Okay. So there is a third case of similarity. Two triangles are similar if they either have the same angles, or corresponding sides are proportional, or, and there is a third case, which goes like this. let me first appeal to your geometric intuition with congruence. So there is a bunch of cases as to when are two triangles congruent. And imagine that you're playing with little sticks, and these sticks are not made of rubber. So that means that you're making triangles, but this side length is fixed and this side length is fixed. And so if these two line segments length are fixed, once we and you imagine that we connect the two tips, basically this angle enough. So two triangles are indeed congruent if this side is the same, this side is the same as and the angle in between those two are the same. So for similarity, all we have to say that these two sides are congruent and the angle in between is the same. So that's the third case. So two sides are proportional and the angle in between is the same. Maybe not today, maybe a week from now. I'll show you an example when that comes up. Okay, so I want to stick with more of these when we chase down angles and then we use similarity to find sides, because that's by far the most frequently occurring one. So here is the thing. Not every triangle does that, but right triangles do something funny. Imagine that this is a right triangle, and let's imagine that this here is, well, I don't know, looks like 25 degrees, and this here is 90 minus 25, was 65, right? If we know that there is a right angle, there is a 25, that uniquely determines the missing angle. Just add them and subtract from 180. After a while, you're going to learn to just subtract this from 90. So now we're going to draw in the hypotenuse the height or altitude belonging to the hypotenuse. And so we split the big triangle into two cute little triangles. Now tell me, now the height means this angle is 90 degrees. So we actually recreate the angle that we destroyed. You see the 90 degree angle is killed, but it was recreated. What is this angle? Well, we know that this is a right angle. We know that's 25 degrees. So if we subtract those two from 180, we get 65. And very similarly, this is 65, this is 90. So this here has to be 25. And then you see visually what it looks like when two angles add up to 90 degrees. That's what they look like. And so what happened? Only in right triangles. The height belonging to the hypotenuse splits the original triangle into two smaller triangles similar to each other and to the original triangle. Okay, so far so good. So that will create some interesting scenarios. And what is interesting is that there are three triangles, but they're not aligned like before. Like, okay, let's look at the shortest side. The shortest side in the original triangle is this, but this is the hypotenuse in the smallest triangle. And the shortest side in that smallest triangle is this here. And the smallest side in this other triangle is actually the height. There are all kinds of interesting things happening. And so you would not believe that if we know that a triangle is a right angle, and we're given not just the hypotenuse, but how the height splits up the hypotenuse, we can find everything. That sounds strange at first, but in fact, we can using ratios. But it's a little bit tricky to write out the ratios because it's all twisted and turned. So there are two approaches. And maybe the smaller one is to unpack this thing. Let me just give out the labels A, B, C, D. Okay, so here's what I'm gonna do. I'm gonna first copy the middle triangle, middle in size, this one here. So this is D, there is a right angle at D, this is B, and this is C. And once I have the points between C and D, there is H, between D and B, there is 50, and between C and B, oh, that's wrong. You know, side A should be opposite point A. Let's make this B. That doesn't affect H and 50 and then A. That was easy because we basically didn't have to turn it. But now we're gonna draw the same, well, a smaller one, but we're gonna rotate it in a way that it's gonna be aligned with this. So basically we wanna rotate out this little triangle. So the ratios are easily read. So draw first a triangle that's obviously similar and try to stay away from, make these two angles visibly different. So try to stay away from pictures like that because basically you're rendering yourself blind. And so based on the angles, first write down the points. So the skinny smallest angle opposite the shortest side is point C. In the smallest triangle at the right angle, there is point D. And in the smallest triangle, the bigger angle is at A. And now that you have the 2 points, connect them and now you can copy. So AD is actually vertical here, horizontal there, but you find it 18. And then DC is just H. And then the hypotenuse opposite the right angle, or AC, is B here. And then we're going to do this one more time, but with the original triangle. So again, we rotate it out so that they look aligned. And then let's start with the angles. And then based on the angles, at the original triangle, at the right angle, we have point C. At the skinniest angle, we have B. And the bigger angle, we have A. And now you can identify the sides by just connecting the points. AC is B. BC is lowercase a. Really? AB, wait, did I do something wrong? A is the bigger, C is the B. So BC is A. BC, so it is BC. In the original triangle, BC is A. And the hypotenuse in the original triangle, it is indeed AB, and it's 18 plus 50 is 68. So this takes a little work, but then the ratios are so much easier to write down because usually the mistake is that people are messing up the ratio They don't write it correctly. So now what we should look for a ratio problem where you have A over B equals C over D, where 3 of them are numbers and the 4th of them is a letter. Then we can solve for it, right? Like in our example, where we had 4 things, number, and the letter. We can easily solve for the letter. And then you're going to find that that's not that easy. There's just too many unknown signs. Like 18B, HA, that's the other way around. It's 1 number and 3 letters. That's terrible. BH, A50, same complaints, right? BH, A50, terrible. But here is what we can do. We can actually find a ratio where there are 2 numbers and 2 letters, but those 2 letters are the same. For example, look at 18 over H and H over 50. We can solve for H there. So we're going to say vertical over horizontal in the smallest triangle. The vertical side divided by the horizontal side is 18 over H. And the same ratio in the medium triangle, the vertical is H and the horizontal is 50. And now look at the equation. If we multiply, you love to say cross multiply, so I'll give in, okay, cross multiply, fine. Okay, sorry. So we could say we multiply both sides by 50H or cross multiply. Either way, what we're going to get is 18 times 50 equals H squared. So H squared equals to 18 times 50, 900. So H is, careful, algebraically, this equation has 2 solutions. And then we rule out the negative one. Now, the problem basically is over, because if we go back to the original picture, if we now know that this is 30, you can do the Pythagorean theorem on 30 and 18 to find B, and you can do the Pythagorean theorem on 30 and 50 to find A. But just for kicks and giggles, just for practice, we can find this sort of ratio all over the place. For example, look at it, A and 50, 68 and A. That's again 2 numbers and just 1 letter twice. And then with B, where is it? 18 and B, B and 68. Oh, sorry. 18 and B up here, B and 68 down there. So we can write down those ratios. Let's see. So for A, look for A. Sorry, what's the page? A and 50, 68 over A. So if we say the hypotenuse divided by the horizontal side, then in the medium triangle, that ratio, the hypotenuse is A and the horizontal side is 50. And the largest triangle, the same ratio is expressed as the hypotenuse is 68 and the horizontal side is A. And so we got, again, a quadratic equation, but a simple quadratic equation for A squared equals 50 times 68. This is not going to be as pretty, I think. 50 times 68 is 3,400. One thing, you can factor out the 100 and then square root of 100 is 10, but either way, so that would be A. And then for B, that it is B18 and 68B. So that would be the hypotenuse divided by the vertical side. So in the smallest one, in the smallest triangle, hypotenuse over the vertical is B over 18. And in the original, the largest one, the hypotenuse is 68 and the vertical side is B. And surprise, surprise, it's very similar structurally. B squared is 18 times 68. And so B is gonna be the square root of that. Of course, the positive one only. There. And then we can check the Pythagorean theorem and we can check the ratios. But I just wanted you to see that not always, this problem would be pretty difficult unless you draw out this picture. Now, if you cannot draw out this picture, I don't think you can just set up because we could have said the vertical over, not the vertical. Well, all right, I should start next time we don't have an exam with this, how to do this. If you don't want to write out the 3 triangles, but let me point out that if you don't know how to draw out these 3, you're not going to be able to do the other way. This is the easier way. So what I'm going to show you in the future is harder. Okay, any questions? All righty then, I'll stop here. Thank you guys, and I'll see you on Wednesday.